And in problem number 2, we have changed the situation. Now the car is starting from rest and heading east at a constant acceleration of 12 meters per second squared. Notice the unit tells us again and confirms that we have an acceleration. So the velocity is changing. The current velocity is going to equal the original velocity plus the change, or in equation language, v equals v sub 0, the initial velocity, plus a times t. V sub 0 is equal to 0. The phrase starts from rest is our cue in any of these problems that, that we're using v sub 0 is equal to 0. We chug through the equations. This is now kind of plug and chug. V at each time is equal to v sub 0, 0, plus the acceleration, meters per second squared, times the time, which has units of seconds, seconds on top, second squares on the bottom. You get only partial cancellation, and now you have a velocity of 12 meters per second at 1 second time. The velocity is in, of course, the expected units. Same sort of thing here. Notice that with the acceleration, you have a pretty fast climb in the velocity. For part B, you could, of course, use an iterative approach to finding the position. This is the way of madness. Don't do that. So instead, use the position equation that we gave in class. X equals x sub 0, the original x position, plus v sub 0 times t. This part here is the change in position which is due to the original velocity. Since the car is starting from rest, the original velocity happens to be 0, but sometimes, as we'll see further on, sometimes that's not going to be 0. The original position is going to be 0 as well, because that's a convenient way of having things drop out. The final portion of that position equation is 1/2 times acceleration times time squared. Remember from Thursday's lecture, the very brief exposition of the fact that the 1/2 comes about because we are finding that position is equal to the area under the velocity time curve. So that comes about because a portion of that curve for accelerated motion, a portion of that curve is going to be a sort of a triangular area. So once again, you are at this point just plugging some things into equations. Presumably you've done that okay. I want to call attention to the fact that now we have a acceleration in meters per second squared times a time, which is squared, second squared on the bottom, second squared on the top. Sorry, let me use more professional language here. In the numerator and in the denominator, second squared, tops and bottoms canceled, giving us units in meters. Since we're asking a question about distance or position, that is the expected unit. Once again, please notice that I'm very consciously checking on our units to make sure that everything is as expected.